So let's start. Welcome everybody to this first afternoon session, and today we'll talk you about the art of schema dissection, operation data engineer. Uh, so first of all, let me present myself. I'm Nino. I'm an Italian and in the art finished that big data engineer at Agile Lab. We are a consultancy firm, and so we're building data systems. In this company, I have the opportunity of wearing different hats, and for my data stacks pipelines, I've used mostly PySpark, Pandas, and Polars. This talk is loosely based on this book by Bill Hinman and Francesco Puppini, the Unified Star Schema, and it applies to all these three frameworks as well. This is something that I measured with the experience, and this is the kind of mental framework that I wish somebody introduced me to when from day zero. So let me explain. Picture this: you come back from your holidays, your previous project is done, then your manager comes at you and tells you the business team wants to be able to see trends in data. They want to see the old record history and be able to analyze the finest details of weekly, monthly, quarterly reports. So we need to build a dashboard. You need to build one big table. One big table. This is the kind of monster I'm talking about. Table filled with data, lots of columns, quite opaque. So you're gonna hit this a lot. Raise hands if you find yourself in this situation. Okay. I see a few hands raised. For the others, I hope this is going to be useful whenever we're gonna be faced with this task. So when they tell me let's denormalize everything, this needs to be quick. I was what? The normalized table? Aren't those an ante pattern? And then 100 columns. What? What am I supposed to do here? So let me stop a second and let me explain why the customer might be wanting this kind of tables. First of all, they are fast to be loaded in dashboards. They retrieve data in milliseconds latency, and second, they are optimized for the stakeholders. So the node joins are required. Maybe the stakeholders doesn't have the capabilities to do that, or is just busy doing the analysis, so it doesn't want to be messed with that. So this make the stakeholder happy, and this is the use case I'm talking about for one big tables. So again, this is not a recipe for every table, only those that are very large and contain the normalized data. Still, these kind of tables are hard to build, not hiding that. But let's not panic, and let's try to break down things. One thing that makes this kind of table confusing is that usually one row contains many entities. And with many entities, there is a source of confusion, and there is going to be a lot of redundant data. So columns that looks the same horizontally, but this is fine. The problem comes in when the repetition comes between different rows. So duplicates in the rows could create confusion. There might be multiple source of truths. You don't know which one to choose. But even worse, you could lose data because the normalization makes it so easy to do that. Still, this kind of use case is not wrong. It's just opaque. Another thing I want to talk about is that tables are leaky abstractions. What do I mean by that? A leaky abstraction is an abstraction that promises simplicity, but still fail to do so for every detail. So it's designed to expose patterns, but then there is structure that is hidden, not in plain sight. The naive design model can lead you to a lot of work later on. So normalization, change data capture, things like that. And to optimize them, you might need different techniques that are not coming straight away at the creation time, talking about indices, sharding, partition, views, these kind of things. But whenever you face with this task, you have to understand that there is a journey of the data. So you start with an online transactional process, one where things, tables are optimized to be written, so to save stored records, where everything is nice and normalized and possibly one-to-one with the objects. Then you go through the dimensional modeling. You choose a schema for modeling your data, and then you end up in the realm of online analytical processes. This is a realm where everything is read optimized. Data is aggregated and then normalized, and OBT are the outcome of the journey. So let's get down to business. Let's pass me the scalpel. I will introduce you to the table. So that monster we saw in the first picture, it all looks the same, but there are organs in there. Not every column plays the same role, even though they look alike. First of all, we have principal keys. So these are the business entities, the business qualifiers that helps you identify the object of the research. There might be more than one candidate, and so they also get the name of candidate keys. And in fact, you can use more than one together in a composite key. Whenever this is the case, you can always reduce yourself from many principal key columns to a single one using a surrogate key. A surrogate key is just a random string or auto-incrementing integer, or even better, a hash of the columns that form the composite key. Then we go to dimensions. Dimensions describe the attributes of your data, the who and the what. They are subject to changes. They slowly creep in different forms. And an example of this is customer country. A customer might move to a different place, changes phone number, or the product that was first categorized as brand new becomes obsolete. And so this could change. Then we have measures. Measure tells you what happened, and they are point in time metrics, numbers. They are also called facts. They might have more than one time granularity. So you could have a measure that is associated to a weekly or a monthly or quarterly time grain. And this is the thing. Measure and time granularities get aggregated together. So they are joint. The mathematical operations are going to be performed on them. You might average them, sum them, perform moving averages, moving sums, and technical fields. These are metadata or columns you use to debug, to join tables together, and these kind of fields usually are on you. So these are the two most, let's say, critical kind of structures, columns. So you see the table that at the beginning was gray, now it's colorful. I hope you have a new kind of way of seeing them. And you might say, okay, but so what? Yes, let me outline a plan. So first of all, speak with your customers, stakeholders, try to understand what's their need, because the wrong understanding, the wrong assumption will lead you to headaches downstream. Then you will start with the entity relationship diagrams, time series, or other data marts, so other big tables that could come as denormalized. I mean, while the normalization is good for a dashboard, it's bad for you. So if you have the normalized tables upstream, renormalize it. Then you choose a model, and you analyze. This point is often undervalued, and It's very important though to analyze the cardinalities of your relationships, because these are going to affect the way you glue them together in the one big table at the end. So let me pick the entity relationship diagrams case. You have these many tables. They might come from different applications, different verticals of the company. Still, they have a graph embedded in them. So the foreign keys in one table point to principal keys in another. And this is a directionality that is important because it tells you who acts on what, who owns the relationship. So you have to stitch them together. Normalization is not just about dissecting table, but it can be used to join them as well. So there are a lot of levels, like 7 or so in the literature, but for online analytical processes, you're gonna need only 2 of those. The first normalization form tells you that you should have just a single value in a column, so no comma separated values in a field, and not duplicated rows. So composition of primary keys that identifies the grain. The second number form tells you that you should have all the attributes depending on the entirety of the key. When you have a composite key, then they're probably sales, products, shipment stitched together. Not every one of these entities will depend on the entirety of the key, but you can still surrogate it, transform the composite key into a single principal key by using the technique I showed you earlier. So these steps will guarantee you safety from insertion and deletion. Data might be updated, and that's not going to be safe, but in an all-up setting, you shouldn't be caring that much about that. So let's come to the modeling side. I'll talk about the star schema only because it's one of the most widespread, maybe not the best, for all the use cases. In the star schema, you have fact tables and dimension tables. Facts sits in between dimensions and describe the events and collect the measures. Dimensions are, again, the description of the actors, the attributes they have. Dimensions should be stable when connected to a fact. And by this, I mean the columns shouldn't change. If that is the case, then consider separating them into into satellite dimensions. So, for example, the email and campaign over there, those dimensions are probably going to change in the future. You keep it in a separate table, and then you just point to the most updated value. This will move your schema modeling from star to snowflake schema, but that's not the topic of this talk. Then again, when a dimension links together multiple facts, it's called conformed. This is a technicality, but it might come up later in questions, so this is why I mention it here. And you can see the date dimension here is shared between multiple facts. So let's get down to the analysis of cardinalities. Some cardinalities are wonderful, like the one-to-one cardinality. When your country has only one capital, then there is no room for this ambiguity. Again, one-to-n cardinalities or one-to-many are also okay, in the sense that everything should behave normally, with a few exceptions. But many-to-many relationships are going to be troublesome. So whenever you have a table that has many other entities connected to it, I think countries have many citizens, and one citizen can have multiple nationalities. So then you introduce a separate entity to remodel this many-to-many relationship into a link of one-to-many relationship. So the passport gives each citizen well-defined nationality when traveling. This is called a bridge table or association table because it describes these kind of things. It's formed by stitching together principal and foreign keys of the two databases into a new one, the two tables into a new one. So now we join. Fantastic. And this is where things goes out. So the problem is that the join operation is a tricky one. Join have side effects. Inner, left, right joins can both lose records whenever a foreign key is not pointing to a primary key of another table, or can create duplicates, as we are going to see later whenever there is a multiple cardinality. You can, if you're experienced with joints, then you think, okay, but outer joints can alleviate this problem. It's true, but all joints have one big problem, that they lose cardinality. By joining two rows together, you put columns side by side, and that loses the directionality. This is when union bridges come into play. So a union bridge is a kind of table that stack columns together on the side, but rows are just laid underneath each other. In this way, you preserve the directionality of the relationship, and you are ensured that all the data is present here. So, for example, let's have a look at these two very simplified tables, the sales and the product table. The sale contain only one entity, so there has been only one transaction here that has involved two products, and the third one was left outside. So whenever a join is going to merge these two tables, I mean, not talking about outer joints, but other joints are going to lose out the third row in the product table. Whereas in the union table, everything is going to be there, and the yellow column is not actually part of it, but it shows you that no values is going to be lost. So let's deep dive into how duplicates creeps in. This is the fun trap. So whenever you have multiple cardinality, there is the chance that when joining things together, you're going to, and measures are involved, you're going to duplicate rows. If you average over them, if you sum them, then it's highly likely that you're gonna get the wrong numerics. Fun a mnemonic for this kind of problem is straight in the diagram. Oops. You see the oops. All right. You see the right part as this crowfoot kind of ending, and that's reminiscent of a fun, the kind of gizmo that your grandmas used to keep cool in the summertime. So many spokes can create duplicates. Another kind of trap is the chasm. The chasm trap occurs whenever two dimensions, two satellite dimensions, are joined together into the initial one. So think of social media like LinkedIn or whatever else. There might be users that have several skills and they might have had several jobs. If you want to create a reporting table that denormalizes these three into one, if you use join in the wrong form, the worst case scenario is that you are going to have a Cartesian product of the two values. So if a user has n skills and m jobs, the outcome is n times m rows, a quadratic explosion. Whereas with unions, you only have one occurrence of them each time, so at most you get the sum of these two rows, and the growth is linear. The last kind of trap is a scenario in which, for example, you have three tables that are horizontally connected together. So think of a sale, like your customer has bought three products, then they are all shipped together into one shipment, and then you might want to join the shipment back to the products to get more details about the whole outcome. You might want to know, maybe here is not shown, but products might have tags, and so you might want to know how many shipments of a certain category has been produced. This kind of joins are tricky because you can have two different paths. You can use the two relationship of shipment to sales to product, or you can join the shipment directly to the product table. This ambiguity can lead to errors, and more some SQL engines are not able to choose the correct path, which might be business dependent, or might as well fail to compile a query plan altogether. And so this kind of problem is one of the most common because it occurs every time there are more than there are the same number of relationship as your tables. With the three tables, you can have at most two relationship. That doesn't create a loop. With three or more, then you're gonna have a loop. But let's wrap it up. This was the Dissection framework. The three takeaway message you should bring with you after this talk are that classify your columns, know them, so that no ambiguities will come. Model your journey into internal hierarchy of tables that then lead to one big table, and then use bridges to preserve cardinalities. So use them as a support to join then tables together. And I hope with this, next time you're gonna face with this problem, you're gonna have a framework that won't make you scared. Thank you. I wanna thank